Okay, so hello everyone, and welcome to our third Aviva Process Simulation training session. So thank you again for joining us today. As we did in the other sessions, I will kindly ask you to keep your microphones muted during all the sessions. If you have any question, please type it in the chat, and we will allocate some time in the end of the presentation to address all the answers. Okay, so Richard, I pass the floor for you for our third day.
Thank you, Brennan. Share my screen and then we will get started. Okay, so for today's session, being the third session, we're going to be focusing on some model library management topics. This is just going to talk a little bit about model libraries and how to work with them as a whole. We touched a little bit about that in the prior sessions, but this is going to be a little bit more in-depth detail on those topics. And then we're going to get into some individual model concepts. These are going to be things like what a connection model is, reference streams, performance curves, factors when it comes to splitting or mixing flow. So there's a couple of concerns there that go across different model libraries, different models that we want to talk about so that way you understand how they work within the software. And then we're going to finish today with discussion on very specific topics useful in this year's academic competition specifically. So we don't have normal reactors in this year's competition, so you're not going to need to do anything like create a reaction submodel, but we are going to use a Gibbs reactor, and we do need to talk about how that works because that works a little bit differently than most traditional reactors. So we'll be talking about that, and then we are going to talk a little bit about how to solve recycles in case you have a recycle and you're struggling to get it to converge. And then we're going to finish today with topics related to the renewables model library. I do a brief overview of what the renewables library is and show a couple of examples that you guys can use as reference to better understand how to use the library. I don't suspect that today is going to go the full 2 hours. So very likely we'll end a little early and we'll take our Q&A early and we'll end when we end. Okay, so let's talk about some model library management topics. When we're talking about model libraries, we're talking about these buttons that you click to start a new simulation, but specifically these buttons are referred to model library templates. All right, so when you look at the software and you go up top on the start menu, there's this area here for simulation templates, and you can pick from one of the 5 different templates. There's also a 6th, which is for being able to access all of the different libraries on your machine at once. But starting a new simulation using any one of these templates automatically creates the file with that specific templates model library as your main access point for units measure and, or not units, unit operations and other pieces of information. All right, so these are our standard ones that come already installed into the software, but there are other model libraries that come with the software. I'm going to briefly summarize those in the slides in a minute, and I'll show you how you can go about importing them and accessing them if you do want to use them for any particular reasons. For this academic competition, the only model libraries you should need are the renewables model library and the process model library, but knowing what else is available within Aviva Process Simulation will broaden your knowledge and capabilities with the software. So we're going to talk a little bit about what those are and what's available to you. All right, so before we get a little bit about model library management, like actually manipulating model libraries and working with them as a whole. This area off to the left here, we refer to as the model library manager. So this is the area where we go to manage all of the different model libraries that are on our install of Aviva Process Simulation. Every tab that you see here is a different model library. All right, so I talked about this the other day. Every model library is nothing more than a collection of different equipment models, fluids that are already predefined, performance curves, which are predefined, and we're going to talk about more today, and then submodels that may be used in your equipment models and other areas. All right, so the model libraries typically are themed around a particular process. And so everything that you're going to find in the model library is going to be designed to adhere to the theme of whatever it is that it's representing. And as such, when you look at models, especially models that you see across different model libraries with the same name, like a valve or a pipe or even a drum, right? The way that they're designed in any one given model library is going to be unique to that model library compared to the way they're designed in a different model library, because every one of these has different assumptions, different factors that it's trying to account for. And so that's going to change the way that these models are written. We go to the model editor window, right? These models have different equations and different variables and other information in this model editor area, depending on the model library that they're a part of. All right, so the first day I talked about how to find help on these models. And you're going to right click on a given model and you're going to go to the help documentation for that model in that model library. All right, so this is the drum in the process model library. And that's important because every model library might have different, changes to the models. All right, so let's take a look at that, and we can see how this works in by looking at some of the other model libraries and comparing some of the common models. All right, so if you come down here and you click on the plus sign, you can click Show Hide Library. And what this does is it allows you to show or hide other model libraries that you have installed on your machine. So right now I'm showing all the ones that you see here. They all have the check mark next to their box. But let's say I wanted to show the cooling water and the flare model libraries. I can check those, click OK, and now I see those model libraries as well here. All right, so now when I come here and I look at these, let's take the pipe, for example. All right, when I right click and I go to help on the pipe, I can see that the help documentation tells me that this help documentation is for the pipe that exists in the process model library as well as the steam model library. So sometimes it's the same, sometimes it's not. All right, and in here, there's very specific information about how this pipe works and the types of parameters and variables I might see in the pipe for this specific model in this model in these model libraries. However, let's go to the cooling water library. Cooling water library is a library that assumes incompressible flow. All right, so when all these models are created, they're stripped of any other equations that might be necessary for, say, compressible calculations. All right, and so when you look at the pipes help menu here, it looks a little different. All right, slightly different information here, slightly different information down here. All right, and then if we take this a step further, let's look at it in the flare library. All right, so here's a pipe in the flare library. And here you can see there's a lot more information here, right? And there's more parameters and variables of interest in here because the way that the flare library operates requires more information than what the other model libraries provide, right? So it's always important to make sure that we understand that the models that we're using in a given model library are following certain assumptions and they're there to support the purpose of the model library that you're selecting. Okay. Now, if there's a model library that you want to have access to and you don't already have it imported or on your machine, you can click this and go to Import Library. Now, this will be grayed out as well as creating a new library if you're in Simulation Building Role. In Simulation Building Role, you'll see it's grayed out. So you need to be in model writing role to expose and be able to import or create your own library. When you do import library, you can go, the default location that opens is this one here. You'll see an examples folder. And when you come in here, you can find all of the different libraries that come with Aviva Process Simulation. And when you look at this list, you're going to see additional libraries that you don't have here in this list of 5 libraries, or even on these tabs over here, right? So when we look at this, we see there's an absorption library, a batch distillation library, a heat transfer library for doing rigorous heat exchanger modeling, right? There's a membrane library, a preview library, rate-based distillation library. Down here, we have a settings library, which is for accessing tuning parameters for your solver settings. There's a transient flow library as well, right? So there's additional libraries that exist here that don't exist automatically and imported and accessible to you on your machine. All right, so importing one of these will put it into your machine, and then you will be able to access it and use it in your simulation files. Now, one thing to keep in mind when you're talking about managing your libraries is that everything is on your machine, right? So all these different libraries are just on your install, right? Some of them are automatically opened and imported already whenever you install Aviva Process Simulation. But if you import one of these additional ones that wasn't already imported, such as the absorption library, that's on your machine. Someone else isn't going to have that unless they also import it first, right? So then if you start making simulation files, SimX files, and they use these additional libraries or even custom libraries that you've created, and you give them to another user, they are going to probably get messages about how it's the file, the simulation file, is missing certain models that they don't have because they're missing those libraries. All right, so you do have to remember that if you do decide to use any of these additional model libraries or create your own model library, you will often have to share a custom library by exporting it to a libx and sending them the libx, or you will have to tell them, oh, I'm using the absorption library. Please import it first, and then you can use the SimX file, right? So that's a little bit about managing the libraries. The other thing to note down here, and I keep saying, is you can create your own custom library. And if you do that, it basically just creates a tab, and I do have one here, so I'll show it. So this is a custom library that I created for one of our training exercises, all right? And it just creates a blank tab, right? So you'll have a tab here, you can name it whatever you want to name it, and it'll be blank, similar to how the simulation model library is often blank when you first go into there, right? And then you can add your own models and information that you want to add in, just like you would the simulation model library. The difference between the two is that this will be accessible by all of your simulations on your install. So every one of your simulation files will be able to access your custom library and get your customizations. However, they're not stored in the SimX. So when you export to a SimX, that information is not stored in there. The reference to this library is noted, but the actual models themselves are not stored, right? Whereas the simulation specific model library stores all of these custom models in the SimX file itself. So when you create the SimX, that's the only file you need in order to replicate everything in your simulation. All right, so I'm going to quickly go through and tell you what all the other libraries are and explain the ones that are available within the software. These are the 5 that appear by default as starting templates. The cooling water library is typically used for cooling water networks, so that could either be distribution networks or gathering networks. Typically, when you do this model library, you're looking at modeling incompressible flow. That's what all the models are designed to support, and it can be used for other incompressible flow other than just cooling water. All right, so if you have other types of incompressible fluids, you can also use the cooling water library. And the steam model library is for just that, steam applications. Typically, these are going to be steam balances, but you can do steam distribution and gathering systems similar to cooling water systems using this model library as well. The flare model library is for modeling flare systems. So everything from your pressure safety relief valves on all of your different equipment, all the way to the outlet flare stack. These are going to be typically large piping systems where a bunch of pipes from the different safety relief valves are going to be either coming together at different points and going towards a flare, or even within that network, there could be distribution and recycles and other things that make the flow a little bit more complex. Right, but this is all about trying to simulate everything that's happening in the flare and all the safety related concerns that go into flare systems, such as back pressures on relief valves and making sure your lines are adequately sized. The process model library is the one that we've been covering for this training, which is the one that's the most versatile model library. It's used predominantly in chemicals and refining applications, but one of the things about this model library is because of the way it's designed and the types of models that it has, it's also usually the library that you use with other model libraries that are either more specialized or specific to a certain type of process. So what you're going to see, especially today when we talk about renewables, if we're talking about the electrolyzer in the renewables library, well, you often use process models in association with that electrolyzer for the process side of the electrolyzer for the production of the hydrogen. All right, so even though there are a couple models in the renewables library that are more process models and not renewables models, electrical models, most of the time you end up going to the process model library and you actually create your simulation, or you can create your simulation from the process model library and incorporate it over. All right, so and you'll see that with some of the other libraries as well. The renewables library, which we're going to talk about later today, is for modeling renewable energy generation as well as green hydrogen production. We're going to focus mostly on the green hydrogen production aspects of it in regards to this competition, but you will need to understand the electrical models and how they all work together in order to support the hydrogen production. So you'll see all of that as we discuss that later. And then we have some of those advanced ones that I talked about as I was going through that open window. Rate-based is for rate-based distillation. This is a non-equilibrium based way of simulating a column, the distillation column. Batch is for batch distillation. It's for doing full startup to shut down batch operations of a distillation column. So usually you have a pot that you charge with your feed, and then that boils off over time, and eventually when it runs out of that feed, the run ends. All right, so that's mainly what this batch model library is used for. There's an adsorption library, which is typically used for pressure swing adsorption. So a lot of times when you're trying to get higher purities that you can't achieve through other more traditional ways, you can use pressure swing adsorption to kind of get you over those, those limits that you'll find in the separation process. There's also a membrane model library. This is one of those examples where you use this in conjunction with the process model library, right? Because if you go into the membrane model library, the only model in the membrane model library is the membrane model, right? And so it's actually a very rigorous semi-permeable membrane that can also support reactions. So it's a very, very in-depth membrane model that's available to you through this library. But in and of itself, you can't just use this model library. You use the process model library to set up your sources and sinks and any other models you want to incorporate in conjunction with the membrane model. The transient flow library is typically used for water hammer or pressure surge type applications and or tube rupture and heat exchangers. What's unique about this is that a lot of these processes all happen on a very small time scale. And so we're talking about thousandths of a second. And so when you use this library, its predominant mode that you use is dynamics. And in dynamics, the step size, instead of it being 0.1 seconds, which is the normal default, the default is 0.001 seconds. So it's much, much smaller. And what ends up happening is you see these ginormous pressure swings due to basically dead ending a flow from completely shutting off a valve or something similar. And those big pressure swings happen in an extremely short amount of time. And so this library allows you to simulate that. And it's predominantly used for safety analysis, right? You want to make sure that there's no safety related concerns to the peaks in the pressures that are building up in these lines. And then we have the controls library, which we talked about, and the economics library, which we're actually going to talk about tomorrow. But I've showed those on the tabs already. So they come already imported. You don't have to select them separately. They are going to be already accessible to you. And then there's one that's not listed here. The slide would need to be updated. There was a brand new one that I showed when I was in that open menu, and that's for rigorous heat exchanger design. And so we have a new model library that is our initial approach to rigorous heat exchanger design, where you effectively have an element which serves as one sort of segment of the rigorous heat exchanger. Then you can piece together those different elements with flows connecting between them, and the way that you connect it all together changes the way that the heat exchanger is basically internally configured. And so all the elements combined are meant to represent the entirety of the rigorous heat exchanger and what's happening within it. But this is sort of our initial approach to this. In the future, very likely the elements will then themselves become submodels of a singular rigorous heat exchanger, where depending on how you configure it, just like a column, it changes the way that the configuration occurs. So that's where we're at and what libraries we have available. With that, there's nothing more in terms of model library management or anything that I want to talk about. So we're going to move on to individual model concepts now. And the first concept we're going to talk about is this idea of a connection model. Now, the very first day, I talked about how when you have these things on the canvas here, right? These things that we would typically call unit operations are referred to as models within AVEVA process simulation. And then this line here that we would traditionally call a stream is actually called a connection in AVEVA process simulation. The reason why we call it a connection is because it's literally just that. It's connecting the information that's coming out of this model, connection point here, to the information that's coming in the inlet of this model here, right? So it's just a data transfer of what's being populated at that point that's coming out of the model and moving it over to here. Now, what's actually in the stream is kind of minimal. Or the connection, what's in the connection is actually kind of minimal, because all it's transferring is the minimum amount of information needed for the next model to be able to solve, right? And so when we look at this and we open it up and we see all of this different information that's here, right? And we can add more information too, right? If we go and show different things, you can see there's tons and tons of information that we can add to this list, and it just keeps going. So I'm not going to keep adding stuff because it'll be quite long, right? But all this information that's here isn't normally there by default. what is happening is that there is something embedded on this connection called a connection model. And that connection model is taking the minimum information that's there and using it within the model's equations, right? It's a model just like any other model, right? And so it's defined with equations and variables and so forth to calculate things. And it's taking that minimum amount and it's producing additional output in this case that we can see that's more traditional as what a normal stream would be, right? However, this information, 95% of it is being calculated and shown because of the connection model, not because of what's normally there by default, right? So let's show the connection model. We can do that. Let's right click on the connection, and down here where it says connection models, I have the option to show the model that's embedded there. And so I see that there's this model here. When I open it, it says it's the stream model from the process model library. So it's this over here, this model right here, right? And so this model itself has all these different equations that it's using, and also has maybe submodels and other things and defined in it. That's calculating all this information that we see that we typically associate as being a stream, right? However, this information is not normally there. So what's normally there, right? What's the default information that is normally going from here to here, right? Well, now that we've shown this connection model, we can look at either one of these lines, these two connections that remain, and we can see what's normally shown or what's normally transferred. And you can see it's a lot smaller of a subset of information here, right? It's what fluid am I using? Molar flow rate, pressure, enthalpy, and composition are the main properties. There's a couple of other properties for reverse conditions and a couple other things that are required for very specific types of calculations like elevation calculations, right? But outside of that, this is it, right? So if I didn't have this connection model on here and I went into my stream, and in fact, we can do this, right? So if I hide this again, I do have an option here to remove it entirely. So if I remove it entirely, and I'm just looking at this, and I go, okay, let me go see what my stream results are. And so I double click and I look at this, and I look and I'm like, oh, wait a minute, there's no mass flow rate, there's no volume flow rate, there's no temperature, right? What are these properties that would normally be calculated in a stream, right? There's nothing being populated here, right? And the whole reason why is because normally that information is being populated through the stream connection model that's embedded on the link, right, on the connection. All right, so now that we've established what's normally there and what a connection model is, you can see from this list that I'm on, we can make this connection into many different types of connection models. There's many options that are available to us here, right? So instead of maybe a stream, what I could do is I can make it a pipe. And now when I come in here, it's an actual pipe, right? You can see, here's my pipe information, right? Fittings information. It's the same exact thing as this pipe model right here. It's as if I took this and put it on the canvas. But because it's embedded on the connection, I don't see it. It's not cluttering my canvas. I'm just assuming that every stream has a pipe, that every stream is a pipe, right? So I don't need to see it if I'm under that assumption that every stream is supposed to be a pipe, right? And so I can come in, I can enter its information, but I don't need to see the model on the canvas. And that's really the whole purpose of the connection model, is that you don't want all these miscellaneous models that are kind of used in a sort of redundant way for just either property calculations or you have like 100 pipes in a simulation. You don't want them all over the canvas because it's going to start to look really bad. It's going to look very cluttered and it's going to be very hard to navigate, right? And so we use these connection models to declutter the canvas and make it so that the information is embedded into the connection itself. All right. Now, every model library has a different default connection model. So when I'm in the process model library and I make a connection, I get a stream model by default, right? So if I make this new connection, I get a stream, right? But if I'm in the cooling water library and I make a connection, it didn't do it. All right, because I actually created this file with I created this file in process model library. So they share the same port type. That's a discussion for Friday. When we talk about model writing, I'm going to talk about something called ports. And that's going to help you better understand connectivity between models and what that minimum information is that's transferred and why. The cooling water library and the process model library share the same port type. And because of that, since I'm using it in the same simulation file, it uses the connection model that I used by default for that port type. All right, so if I go to this, which is a cooling water file, and I add the models down, oh, and I'm in load flow there. Now I get a pipe, right? So now I have a pipe here. Okay, so every model library is different. The process model library uses the stream model. In the renewables model library, you're going to find that it's going to be a specific thing that reports something related to your electrical information for your renewables grid. Right, so it's slightly different. It's not going to look like a stream because it's not that type of information to begin with. So you'll see it's different in that model library. All right, next thing I want to talk about here is reference streams. So one of the things that you can do within the software is you can create a reference stream by exposing the, and we'll do this one, exposing the stream model connection model. Right, so I have the stream connection model shown now. And if I have another source, I can go from the connection model and go into the, oh, sorry, that's a cooling water source. I need to process. Every model library is different, right? So process model library is the one that has this. Right, so I can go into the process model library source. And now this source is going to use whatever properties it is pulling from the stream connection model. Right, so you can see the property information is the same between these. Now, this is what it means to be a reference stream, right? So it's referencing this here is referencing this stream model. All right, and what's good about this is that, let's say this is my main network. And for some reason, I need to do some kind of side calculation that involves this stream here. Well, for me to be able to pull this stream off and do my side calculation would mean to disconnect from here and drag it into my side calc. And then everything from this point forward is going to go unconverged and be problematic. So if I have this reference stream instead, I can leave my main network undisturbed. And then I can just use this and build out what I need with my side network in order to do the alternative calculation here. And what's nice is that I can overwrite what I'm referencing. I don't have to use the reference values. So if you come down here to where it says reference, I can change it from reference to source for any one of the conditions that you see here. And when I change it, that property will become specified. And now I can change the value. And so I can have a different value here than what's in the referenced destination area. Right. So this is how to do reference streams. All right, next thing we're going to talk about is performance curves. Now, for your work with this academic project, where this might end up coming in is for some of your renewables curves when it comes to power generation for, say, a wind turbine or a solar farm over the course of a day or versus the wind speed, something along those lines. You're going to want to create a curve that relates the power to those different properties, right? And then use it within the model so that it has a more accurate representation of the power calculation, right? So this is probably where you're going to end up using this capability, but anywhere where you have some kind of curve or relationship is going to use this same infrastructure to create a performance curve, right? So a performance curve is created by either copying an existing curve, so I could copy one of these ones that's already here, or by creating a new one from scratch, create a new curve. And that's what we're going to do here, right? And once you create the new curve, again, you should do it in the simulations model library, just like the fluids, right? This is very similar in the way that fluids work. You can double click or right click and click edit to open up the curve editor window. So this is a specific editor window just for curves. And I recommend typically when you use this, that you expand it out so that way you can see the entire plot over here. And this is going to be a large portion of what we focus on here with the performance curve. All right. But in order to get started with this, we need to do a little bit of setup. All right. So we have a pump that we're simulating here. Let me scroll over. See if I can get this in view real quick. Sorry about that. Okay, so we're simulating a pump here, and inside the pump, there is a spot where I have this curve type parameter. All right, so any model that has this curve type parameter is typically going to be something where you can select a curve model to be used for a specific relationship within the model. Now, with pumps, there are a couple different ways that we can set up the pump curve, right? We can either do, let's say, your volumetric flow versus your head. You can do volumetric flow versus MPSH. You can do volumetric flow versus efficiency. So there's a couple different ways that we can set this up. But typically in these curve windows, the way that we set it up to start is we have one independent variable. In this case, it's going to be volumetric flow. And then you can have as many dependent variables as you want. So the dependent variables are going to go against the independent variable. And for each one of these that we set up, we can define a different curve for that relationship. All right, so I might want to go Q, and I have to tell it what type of variable it is, because right now it doesn't understand that it's volumetric flow rate. So I'm going to tell it it's volumetric flow. And you notice the units of measure are internal units of measure here, and you can't change them, not at this point here. All right, we can change these units of measure down here though, and we will when we get to that point. And then we're also going to set this up with head. So we go, hold up, not hydraulics, yeah, liquid head. Okay, again, we're going to leave it like that for now. All right, so we could set this up for multiple properties if we wanted. So let's say we did efficiency as well. Efficiency is normally defined as fraction. So we'll leave it like that. And then for every one of these that we define, when we come down here, we can pick what we're defining, what curve we're defining. So right now we're defining the volumetric flow versus head, but we can change it and we can do the volumetric flow versus efficiency. All right, so we can do a different curve for each one of these relationships. For now, I'm going to leave it like this. Now we're going to set up a volumetric flow versus head curve. Now, in the end, in the very end, when I'm finally done with all of this, the only thing that matters is this table here, making sure the table is right with the correct values, right? And then in the correct units of measure. That's what's important. right? But there's a couple different ways that you can create this table, and it's really going to come down to preference. One thing that I could do is I could come in and I could start typing in values, right? And I don't know if these values are reasonable. I'm just typing in values here. So I can type in some values. Again, I'm just adding points. I know they're not reasonable, so don't judge me on that. This is going to get fixed in a minute. We can create this table manually by adding rows and entering the values. And as you can see, as I entered values, it started to populate a curve here, right? So that's one way that we can do it. But Aviva Process Simulation has a much more friendly way of doing this where you don't have to manually type everything in. And it's for your sort of long-term benefit with the curve. And that's, you can import an image, an actual pump curve. You can use that pump curve to help set up the points that it's going to use to define this table. All right, so we're going to do that real quick. We're going to browse for a pump curve. I'm going to go right to our training material here. So just give me a second. See if I can find the file offhand. Yeah, here we go. All right, so I have a pretty standard pump curve here. It's just an image file that I imported. So if you have a JPEG, PNG, like whatever the file type is, even a PDF, you can import it here. The biggest thing is usually just trying to make sure it's reasonably straight, right? You don't want this to be crooked, and you're going to see why as I move forward here, right? But you want this to be relatively straight, you know, when you're looking at it. Now, once you have the image imported, the next thing you need to do is set up this blue box, which is going to be the area that the program is actually evaluating. This is the portion of the curve that the program is looking at and actually interpreting for the information. All right, so when I set this up, logically, what makes sense is to set it up starting at 0, 0 and go all the way to the other corner of the plot, right? So that's one way that I can do it, but I could also do like this if I wanted to, right? I don't have to go all the way up. I don't even have to start at 0. I can go like this, right? What's going to be important is that wherever I draw this box, that I set up my boundaries for the y-axis and the x-axis so that it properly interpolates the values in between on the box. All right, so these are going to be the starting and ending values for the box itself. All right, if I use this right here, all right, and let's say I come down for my volumetric flow rate, I'm going to use the gallons per minute values. All right, so the first thing I want to do is I want to change this to gallons per minute. I'm going to have a value of 0 up to 2,000 gallons per minute. So 0, 2,000. All right, so that's for my x-axis. My y-axis here, it's not going to be 0 because I'm starting my box here at 25, right? And it's not going to be up here 150 feet. It's going to be 125 because that's where my box ends, right? So it's all about defining where my box is along the graph, right? Now I am going to extend this back out so that we can see the whole plot. And as such, when I do that, I want to make sure that I'm inclusive of these points now, right? So I'm going to use the feet values. So go over here, set the feet. This is going to be 0. And this is going to be 150. Okay, so now I've imported my image. I've set up my box for the area that I want the program to look at. And I've set up my boundaries as far as what those values are. Now I can come back here to my curve, and what I see is actually the portion of the blue box that I've set up, right? And you can see here are the values, 0 to 2,000, 0 to 150. And what I can do from here, and I'm going to delete these other points just so they're not in the way as I do this. I can hold Control on my keyboard, and I can just click on the plot to add the points. And by doing this, I can trace this line in the background, which is my head curve. So I trace this, and as you can see, every time I add a point, this table over here is populating with the points values, right? So I can take this all the way out like this. I can add another point here just to make it cleaner. And so that I get rid of this spike here, I'm going to delete this first row. All right, so now I have a curve, right? And it was much easier to enter because I didn't have to type out all these values manually. I just set up my image and then I followed the image. And what's good about this is now you have this curve set up. You have the image in here already. Let's say in the future, you need to come and revisit this, and maybe you need to use a different one of these curves, right? It's very easy for you to just go from here and take this and drag the points down, as opposed to retyping in a new set of table data or creating a new curve from scratch, right? So you have different options that are available to you here to make your data entry easier and your management of your curves a lot easier within the software. All right, so I'm going to do this. I'm going to delete the last couple points. To delete a point, all you have to do is hold Control and click it again, and that gets rid of it. All right, so we'll leave this curve here. The next thing I want to show is that there are ways of adding multiple curves for the same property. So if I wanted to, I could add in a new curve set. And we're going to say speed in this case, right? Right. And down here, we're going to define the different speed values that we're going to evaluate this at, right? So I could be looking at, this is RPMs, right? So maybe there's a 1,000 RPMs, there's a 2,000 RPMs, so forth, down the line. I'll do a third just to see one more thing, right? And now when I come down in this area over here, you can see there's an additional part that's been added. So now I have my volumetric head, or my volumetric flow versus head at a specific speed, right? So this could be set 1. Then if I click this and click set 2, you'll notice I can set up a whole new one for speed at 2,000, right? And so now I have another relationship that I can factor into here and have multiple curves for the same curve properties. Okay. So this is everything with performance curves that I wanted to show. Once you're done with this window and you're satisfied with how you have it set up, you can close, and then you can take this curve and you can use it on your pump or your equipment model in the software. All right, so I can select it here. Now, since I didn't exactly create a decent curve, I'm not going to use it in this file, but if I had, I could use it in this pump. Okay, the next topic we're going to talk about is mixing and splitting flow. We touched on this a little bit yesterday when we were talking about how to transition from one mode to another. But now I just want to talk just about the concept of balancing inlet pressures in models. And so this is for any models where you're mixing flows together. Right? And so there's a couple different things that you want to look for and try to account for when you're handling this. Right now, when I look at this, I have a header here, and it's using the default behavior in process mode, which is that inlet pressures are just whatever the minimum value is that's coming in. So when I look at the two values that are coming into the header right here, I have 675 psia and 625 psia. It takes the 625 psia, right? That's the inlet pressure that it ends up utilizing, all right? If I change this to balanced, it tells the program that both of the feeds in this case, or all feeds, if I had more than two, all the feeds have to be equal to one another when they come into the header, right? So when I do this, the program's often going to tell me that I'm unsquare, and it's usually going to tell me that I'm unsquare by, the number of feeds that you have minus 1, right? So you have to free up everything except for at least one, and that will make it so that everything else matches the one you didn't free up, right? So if I come in here right now and I free this up, then my pressure drop increases through this valve so that this pressure matches this pressure as it goes into the header. All right, and so that's the way that this is normally going to operate when you're working within the software. But you could take this another level. Not only can I set this to balanced, to force it to be balanced, to force it to be equal, I can now control the pressure directly in the header model. So you can see there's a pressure variable here. If I specify this, I can then free up the other pressure drop. Now everything is fluctuating in the feeds, right? Both feeds are fluctuating. And so whatever I set this to, it's going to adjust those pressure drops accordingly to match whatever I have the header set to in this case, right? And so this is the approach that you'll take for any type of model where you're mixing flows like this. So it could be it just has the header in this library. Let me show the process library so you can see some in the process library. Okay, so the process model library has the mixer can mix any amount of feeds into it at once. The header can mix any amount of feeds into it at once. The drum can mix any amount of feeds into it as once. The column has the same type of behavior, except for the column, it's not set to minimum by default. It's set to ignore, because in the column, you want to specify a column pressure profile. And when you specify that, you just want to ignore whatever pressures are coming in so that it only uses what's specified, right? So it has an inlet pressure setting, but instead of it being minimum as one of the options, it's set to ignore, and balance is the other option, right? So any types of models like this are going to have this sort of behavior. Now, there are some model libraries and models that have slightly different ways of handling the same concept. So if I look at the cooling water library and I take a couple of sources, I put them down and I mix them together, the mixer in the cooling water library has two individual feeds that it's mixing. So it can't take more than two streams coming in. So it doesn't have a parameter that manages this. It instead has a variable called p slack that calculates the difference between both lines that are coming in, right? And then you can specify p slack to be 0 to make them balanced. So if I go like this right here and I increase this pressure to 20, I can see P slack is 5.3 because there's a difference of 5.3 psi between this 20 and this 14.6, right? 14.7, right? So what I can do is I can specify this. I can unspecify this, which in reality, you'd probably have a valve. You'd unspecify the pressure drop in the valve, right? But I only have a source here, so I'll do it with the source. Then I can set this to 0, and when I do that, it forces the one line to match the other line. Okay. All right, the other concept here that we're going to talk about with the same file is the concept of out ratios. That's how models like the header and any other models that split flow, like the splitter, some other models around here, when they have multiple streams coming off of them, they need to understand how to distribute the flow between all the different products coming off of the model. right? And so there's this out ratio variable that is in these models, right? And the out ratio variable by default is going to have every one of these specified to a value of 1. So every single product is going to have a value of 1. It's going to be specified, which means they are an equal ratio with one another, no matter how many that are there. So if I had 2 products like I have here, it would be a 1-to-1 ratio. And so it would be a 50-50 split, right? The flow would arbitrarily go 50% one, 50% the other, right? If I had 3 streams, it would be a 1-to-1-to-1 ratio, which would mean it would be 33%, 33%, 33%, right? 4, it's 1-to-1-to-1-to-1, so it's a quarter each, right? And so on down the line, right? But they're always equal. So what you end up doing with any model that has this out ratio is your goal is to typically free up every single out ratio variable in exchange for a condition in one of the products coming off of the model. All right, so in this case, I can set a flow rate that's required in this sink. By setting this flow rate, I can free up this out ratio so that the header sends how much is needed here, and then the rest goes out in the remaining product, right? In an ideal scenario, you have one and only one out ratio specified at a given time, right? But there's a bunch of different ways that we can set this up and for various reasons. I'm going to quickly go to a slide here, which I use frequently to describe this. So this is a similar sort of behavior here. We have a header and there's 4 products. This is the way it appears by default. So I have a 400, we're going to say pounds an hour, 400 pounds an hour coming into the header. And the header is going to split this in a 1-to-1-to-1-to-1 ratio. So it's going to be 100 pounds an hour, 100 pounds an hour, 100 and 100, right? It's an equal split amongst them. However, I can change this behavior by swapping out the out ratios for some conditions in these. And they could be valves, it could be sinks, it could be a turbine, a heat exchanger, a pump. Any model could be on this line instead of what you're seeing right here in the image. All right, and every one of them could have a condition that back requires a certain flow, right? So I could specify the flow outright, which is what you're seeing in this table here, right? I could say I need 100 pounds an hour here, 100 pounds an hour here, 100 pounds an hour here. The rest goes out this one. That's what this green example is showing, all right? But it could also be something like if I had a pump and that pump had a certain power, that power that I've specified will dictate how much flow is required in order to meet that power. And so certain flow needs to be sent to the pump from the header based on the power requirement, right? Same thing with a heat exchanger. If I had a heat exchanger and there was a certain temperature spec or a duty spec that I put in, that's often going to relate to a certain flow rate that's required to meet that condition, right? So the goal here is that all of the consumers coming off of the model are going to have conditions that are back calculating the flow requirements off of the model. So you just free up the ratios so that it can distribute it in a way that's not an equal split, right? Now, there's different ways that we can set this up, but one thing you can't do is specify every single product coming off and also have your feed specified. So I have this red scenario here that shows you what you can't do. I can't have 400 pounds an hour specified coming in, 100 pounds an hour off of each one of these valves specified, and expect that the program's going to solve. It might solve right then and there, but the moment any one of these deviates a little bit just from that solution, it's going to fail to solve because you've over-constrained the solution. You have basically fixed the mass balance here such that it can't solve to anything other than what's specified, right? So this is not a feasible way of setting up this type of behavior. This is why we say in an ideal world, you have all of them freed up except for one. Whichever one is still specified, it really doesn't matter what the value is because it just gets whatever's left, right? It's 100% getting whatever's left, right? And so this is the ideal way of setting it up. Now, you could still work with these out ratios specified and see different behaviors or impose different behaviors. Let's say, for example, I wanted to have, let's do this. I want to have 50% of the flow coming out of this, and then the remaining 3 be equally split, right? I could work with the out ratios by changing the values and set up the relationship differently, right? So there's 6 total values here, but 3 of them, 50% of them, is for this one stream. So 50% of the flow is going to go out there. And then 1/6 of the flow, or 1/3 of what's left, right, is going to go out each of these other 3. Right? So this is another way that we can go about setting it up. We could also, and now I can't do that with this image, right? I can't check this box right now. So let's just assume, though, that I did something like this. Let's say I had 2 product streams that I know need to be in a specific ratio with one another. So I leave their out ratios specified, and I set the value of that relationship here, right? So I need a 2-to-1 relationship, 2-to-1 ratio between these 2 streams, all right? And then I can free these up still. And what happens is these 2 will be dictated by whatever's, coming off of it. And then whatever's left is going to be split 2-to-1. Right? So if it is this that we have here, 100 comes off of the 600, so we're down to 500. Another 100 comes off, so we're now 400. That 400 that remains gets split 2-to-1, right? So it's going to be 266 and 133 in each of these remaining lines, right? So you can force the ratio in that regard if you leave certain ones specified and the values are set properly. This is useful for stuff like columns, where you're externalizing a column condenser and you want the splitter that's returning the condenser reflux to be in a specific ratio, reflux ratio, right? A certain ratio back to the column versus what's going to the product, right? So this is the way that you would go about setting that up in the splitter. All right, so that's going to cover all of the individual model concepts that I wanted to talk about. We're going to move on to the Gibbs reactor. This is going to be a big part of the academic competition project. However, it's not a very complicated model to discuss or really utilize. The thing about the Gibbs reactor is that what makes it useful and what makes it rather unique is that it doesn't require any sort of reaction information or stoichiometry. It performs the reactions based off of the Gibbs free energy of the components that exist in the reaction, right? To the program, let's open a simulation file with a Gibbs reactor real quick. And so I'm going to open up this file, which I've already opened earlier, but if you want to access this file so that way you can learn more about Gibbs reactors, you can do so by going to File, Import, going to that SimCentral Examples folder that's pinned up here, go to Simulations, and then go to Undocumented Examples. And this is the file that we're looking at here, CC10G. There's also a little bit slightly different approach to this that you can look at in this example file as well. And then, let's see, I think those are the only Gibbs reactors that are in here. Yeah, I don't see any other Gibbs reactor examples. So this CC10G one is the one that you're going to want to reference to learn about how to use the Gibbs reactor more if you want a file to reference. Right, so this is the file that we're looking at, and the reaction that's occurring here is this that you see here, which is 1 nitrogen plus 3 hydrogen equals 2 ammonia. And now if we were to write this and do this in a conversion reactor, we would need to create a reaction submodel, some kind of submodel that performs the reactions similar to what you see over here with these electrolytes types of reactions, right? And there's a tool, we'll talk about this on Friday, there's a tool that we can use to help us create this reaction submodel, right? And then in which case you would go into the reactor and you would pick it from a specific option, pull down, you would pick the reaction submodel. But with a Gibbs reactor, we don't have to worry about the reaction submodel, right? We don't even have to worry about the stoichiometry even, right? All we have to do is come into the Gibbs reactor and tell it what components are reacting. And we do that by either setting the value to 0 or 1. If the value of a component is at 1, it's included into the reactions. If the value of a component is at 0, then it's not included. So it's just going to bypass through and no reaction is going to occur involving that component. Now, how does it perform the reactions? Well, I don't have the theory and the expertise to explain it in detail, but what I can tell you is that it's trying to minimize the Gibbs free energy of these components. And so if we look at the fluid here, we can see that all these different components have Gibbs free energy values. So I have to wait for this to load and I can show you. So we go to heat of formation information here, and we can see something's going on. There we go. All right, we can see from this list here the components and their Gibbs free energy of formation. Right, so there's the Gibbs free energy values, right? And so what it's trying to do is trying to minimize the collective values that are coming in from these components. Again, I'm not an expert in this, right? So I can't give you too much more other than that, but that's the goal, right? And so as long as there's some values there with the components, it should be able to perform this minimization, and you will see reactions occur. And it really is as simple as that when it comes to this Gibbs reactor. If there are no values for these components, or the values aren't lined up properly, you might not see the reaction occur the way that you expect because the property information might not be adequate, right? So it's all based off of that one property in the component property information. And then when we look at the reactor itself, there's only so much information here when it comes to the reactor. Right? And I'm in model writing role, so I'm saying more than I need to. Switch over the simulation building. All right, so you can see there's not a whole lot of information here. You can tell it what phase the reaction occurs in. Oh, you do have to set it to solve. There's a configuration mode and a solve. So while in configuration mode, this is typically used to initialize the reactor, get it onto the canvas, get it connected, make sure that it's square and solved. But in configure, there's no reaction occurring. Once you switch it over to solve, that's when it actually performs the reaction calculations. So it's always good practice, and I'll show it real quick. It's always good practice to take your models, put them on the canvas, connect them together, make sure you're square and solved, and you can see this is red because it's in configure mode, right? Get certain pieces of information set up, make sure it's all happy, and then when you're ready to invoke your reaction, you switch it over. Now, for this here, I want to make sure I'm using the fluid in the source. All right. So I got the right fluid over here now. And I switch it over to solve. Right. And it was a seamless transition. We didn't have any issues with convergence or setup. Right. So that's the general idea of how to use this. There's other information here, but most of it's just operating conditions and results that you can check and view to understand if things are going as you expect them to go. You can see here with this one how the results changed with the mass balance here. Now this is ironic because this is mass flow rates, and reactions occur on a molar basis. So don't be deceived by these values. Make sure you're checking the molar flow rates, which is why I set these values out here. That's going to give you a more true indicator of the actual stoichiometry and verifying that the reaction's occurring properly. Okay, so that's it. When it comes to the Gibbs reactor, on Friday we'll talk about the other reactor types and reactions in more detail. But for now, that's really all you have to know when it comes to using the Gibbs reactor. The next part we're going to talk about is the recycle model. We get an example open so we can talk about this. Okay, so the file that you're looking at here is our cumene production simulation example that is in the examples folder. So if you want to reference it, you can go import, go to the simulation examples folder, go to simulations, and then there's this cumene production file here. All right, so you can look at it. I've just renamed it because I use this frequently enough that I wanted to keep it in my repository. So this is the file though, and I didn't do anything other than add this text to the file. So it's pretty much what you see here. Now I'm going to review quickly what's in this file, so that way you get a feel for what's here and the reason why we needed the recycle and what ended up happening. So over here is our feed streams. Right. The main thing with this process is that we are, and I'll zoom in so we can all see this. All right, so we're feeding in this case, propane, benzene is in one of these other feeds, and this other component here is in one of the other feeds. And then as it's going through the process, we have a little bit of a pre-separation treatment that it goes through a little bit of a heat exchanger train and goes into our reactor. And this is where the cumene is being produced. And then the product comes back through the other side of these heat exchanger trains and starts going through our separation train, which is going to be a flash drum here and a couple columns over here. Now, this first column that we have, the overhead of it is going to include unreacted benzene. And so we can recycle this back so we don't have to use as much benzene in our feed. Right? And so here's the other feed with the benzene, and here's our recycled benzene come back into the process. Right? So this portion here, up until the point when this recycle is being connected, is our normal feed. And we are recycling back the benzene that's unreacted and connecting it to this point. Now, when we do this in our simulation, what we recommend is that you just make the connection. If I know I'm going to recycle it back from here, I just connect it back to my feed point and I see if it solves. All right, now we're hopeful that the program is robust enough that it will be able to connect the recycle and report back that it's square and solved and there were no issues. However, this is an equation-oriented software. Equation-oriented softwares are notorious for recycle issues when it comes to convergence. And unfortunately, we don't escape those problems as well here, despite all of our advances that we've made to make it perform better in that regard, right? And so what you'll occasionally need to do is there's a model here called a recycle model. You'll need to put this onto the canvas to utilize this to help you converge your recycle calculations. All right, and so if you make this connection directly and it comes back as failed to solve, the first thing you want to do is undo. All right, you don't have that option in other software, but here you do. Undo, and it'll get you right back to where you were last, where you were square and solved, and it wasn't connected, and you can move forward from that point as your starting point. Right now, once you've undid the connection and it's disconnected again, you're square and solved, add the recycle onto the canvas. And when you put the recycle on the canvas, you're going to want to put it in source mode. Okay, so in source mode, if we zoom in and look at this model real quick, we can see any flow connected into the recycle just stops. And any flow coming out of the recycle is almost like a new starting point. And you can see it behaves like a source, right? We have flow rate, temperature, pressure, and composition all specified here. So it's behaving like a source in this case. And so what we've effectively done by putting this recycle down and putting it in source mode is we've made it so that we can sort of kind of make the connection for the recycle. So we've brought it from over here, connected it into here. It stops here, but we've made the connection over here. And we can manually work with this information here to try to converge the recycle calculations. And so when I put this into the main process, right, when I connect it over to where the feed is over here, where I'm recycling, right now it's feeding in these conditions into the main process. And I can work with those conditions to try to get the simulation to solve. And the goal is to get it to solve so that the information coming out of the recycle, when it comes all the way back around, back to the inlet of the recycle, that these properties closely match one another. I am trying to manually close any differences between these values. That's going to help the program solve the convergence issues, right? So when I do this, I want to have these two windows open so that I can see, okay, I changed this value here. What impact does that have on this value here? And are they close? And my goal is to get these close enough so that I could switch it over to tear and then to normal operation. I'm going to talk about those in more detail in a second. All right. But the idea behind this is that you are manually working with the recycle, basically, coaxing it into the solution that you need it to achieve. All right. So let's take an example of this. I'm going to set a value here of 100. And we're going to say that when I first tried to connect this, it failed to solve. I undid, I put the recycle down, I put it in source mode, and this is what I'm looking at here. And I'm seeing there is a 3.72 kilomole per hour difference between what's coming in and what's coming out. And so I need to try to figure out why there's a difference and see if I can close this gap. All right, I'm assuming right now, despite the fact that this says it's square and solved, I'm making the assumption for the example's purpose that it's unsolved, okay? And so that gap, that difference between the two values is too large of a gap for the solver to be able to solve, right? And so I need to manually get this to close so that these two values are less different from one another. They're more similar to one another. Right, and so one of the things I might want to do is just take the value and use it as the next value that I set. So what happens when I set it at this value? Right, so I set it. I look at the new solution. Okay, now it calculates a value coming in of 105.3. So this isn't a 3.27 gap or a 3.72 gap. This is now a 1.5 gap, right? So the gap got smaller. Right, I'm slowly closing it. And if I follow this, take the next value, put it here, I can slowly work this to a point where the difference between the two values is practically the same. And when I'm happy with how close they are together, that's when I want to switch this over here. Now, what tear is going to do is it invokes a technique that sequential solvers benefit from. Sequential solvers solve recycles a lot more robustly because they make use of something called direct substitution. It's a way of solving iterative calculations. So what happens is when you're iterating, you're calculating the same thing over and over again to try to close a gap like this. You're constantly comparing what's coming in to what's coming out of usually key strategic points within the file. These tend to be recycles, and in most programs, they refer to those recycles as tear streams, hence why this term is called tear, right? And what they're doing is those are normally identified as like the key streams within the entire configuration of your network, that if you were to separate it, sort of how we had it here in source mode, if you were to separate it, you would break apart the recycle in the least amount of breaks, right? And so that's the concept in a sequential solver. That's what a tear stream means. But in here, when we pick tear, what we are basically telling it is invoke that same approach to solving that you would in a direct substitution sort of manner, right? And so now when the solver tries to solve this, even though we don't see this happening, in the background, it's going to run through the calculations. When it comes back to the recycle, it's going to compare what's coming in to what's coming out. And if it's within a tolerance, it says it's solved. If it's not within the tolerance, it goes again. It sends the value once more through the entire network. And then when it gets back, it compares what's coming in to what's coming out. And it keeps doing this until that gap closes on its own. And so you did a little bit of that already when you were in source mode. You were slowly closing that gap yourself. You got it to a point where you're basically telling the computer, take over and do it yourself now. And if it solves, once it's in tear now, then you want to switch over to normal. And what happens here is now it's as if the recycle model doesn't even exist. It literally just passes through the recycle model. There's no iterative calculation that's being forced upon it, like we did with the tear mode. All right. And so this is what you're trying to get to in terms of normal equation of or not equation, equation-oriented solving approach, right? This is going to make it the most robust and behave most accurately, right? But both tear and normal at this point are basically the same solution. It's just tear is going to have more calculations occurring in the background, so it's a little bit more involved in order for it to solve, right? But you start by manually working it towards that solution. Right. Now, let's say you're here, and let's go back to this. Right. Let's say you're here, and you take this first value, and you set it, and you're trying to close the gap. But instead of this value getting smaller in terms of the difference between the two values, let's say it got bigger. Let's say instead of this being 105, let's say it's 110 now. So we went from 3.72 kilomole per hour difference to now a 6.3 kilomole per hour difference. And if we did that again, right, we set this to 110 and it comes back with 120 here. Now we have a 10 kilomole per hour difference. It's getting larger. That means you're working yourself away from the solution. And this change that you keep making, that alone is not going to fix it, right? So something else is happening here that you need to better understand to fix the behavior within the recycle, right? And typically when you see that behavior, it's indicative of a problem with the setup in the larger file as a whole, right? So something that's happening within the rest of the recycle is preventing that gap from closing, right? There's some other condition that's happening here that's preventing it from closing. There's a classic example of this that we use in our Pro 2 training, where we talk about a furnace preheating a feed coming into a column. And if the furnace is too hot, it vaporizes more of the heavier components in the feed. And then those heavier components go up the column, recycle back into the feed and back through the furnace and get trapped in a loop, such that your instead of your column having the heavy components coming off the bottoms as a product as it's supposed to, it traps them in the recycle, right? And so if you had something like that happening here in the software, you would never get that recycle to converge simply by changing a condition here in the recycle model, right? It's indicative of a problem in the furnace. The furnace has too high of a temperature. That's what's trapping the heavier components, right? And so you have to better understand what's happening in your process and go to the area where the problem is once you figure it out and address it there, right? And that's what's going to fix it so that it allows you to converge your recycle, right? So a couple different things here when it comes to recycle convergence. You got to think about the recycle model is good for many things, but it can't overcome limitations in the way that you have the file set up, right? And so if you try the recycle model and it doesn't solve with all the normal techniques that the recycle model would utilize, then you have a larger problem at hand that you need to figure out. All right. I do want to point out here, we have another model here called a closed loop model, and that is used for modeling closed loop systems. And so I have a slide over here. I'll show it real quick. If you have a true closed loop system, meaning you don't have an external feed coming into the loop or a product coming off of the loop, everything is self-contained within the loop itself. So if I look at this image here, and I follow the blue line, even though it splits here and then eventually comes and mixes back up around here, right? It's all one large loop going through all these exchangers, all these different paths. There's no external feeds, there's no external products. And so solving this can be tricky without the use of a closed loop system. It would involve making use of mixers and splitters with external feeds and purge streams that you slowly work towards zero flow in those external feeds and purges to force the flow into staying within the loop. And that's tricky. I've done it before. It's very difficult to do that. However, this closed loop model fixes all those concerns because you can put this into a source mode of operation, just like you would the recycle. And when it's in source mode, you can set up what the fluid is, what the flow rate, the temperature, pressure, compositions are. And then you can use that as your initialization point for the loop. When you get through modeling everything else in the loop and you connect it back to the closed loop, you can switch it from being in source mode to normal operation. And now everything is contained within that loop. Right? So it's a much easier way of modeling a true closed loop system. Okay. So the last topic that we're going to talk about for today is the renewables model library. And this is going to be a big part of the academic competition this year. So what I want to do is start off with a little bit of some background on what renewables model library is typically used for and some of the models that you're going to find, the way that those models operate. And then I'm going to open up a couple of different examples and show you them within the software so you can get a feel for them in the software. All right, so we're going to actually go into slide mode for once and do a little bit of slide explanation here. Okay, so the renewables model library is a model library that's designed for renewable systems. And so typically this is for renewable energy generation and or hydrogen production using electrolysis. We also have things in here for energy storage in a battery, as well as just normal energy distribution and gathering if you want to model basically a full electrical grid. All right, so you have that capability here within this file for doing renewables energy simulation. All right. Hydrogen production is one of the main focuses of this model library. It's going to be one of the main focuses of your academic competition program. And when you talk about hydrogen production, there's a couple different ways that you can produce hydrogen. They typically go by certain terminology that you see here. So there's gray hydrogen production, which is our sort of old standard for producing hydrogen. This is usually done with like steam methane reforming, water gas shift reactions, stuff like that. This is not a clean process, not at all. All right, and so this is something that's starting to become phased out, and it's starting to be replaced with alternative approaches that are cleaner and or renewable. So there's also what we call blue hydrogen production. This is one that tends to be more clean, not necessarily renewable, but is more clean because the carbon that's produced during this process is captured and stored underground. So it's not as much, being offset into the atmosphere. It's a little bit better of a process in terms of the environment. All right, and then we have green, which is not just clean for the environment, but it also uses renewable energy sources. And so when we do it with this, there's no carbon byproducts. And you'll see as we go through, because it's going to be the main focus here, we use all renewable energy sources in order to support this. When we look at some of the ways that Viva Process Simulation, I'm just going to show all these at once. Viva Process Simulation handles the different ways that you can do hydrogen production. You can see from here, and it's color coded to match those color codings that we just talked about. But we can handle all of it, right? We can do gray hydrogen production, green hydrogen production, blue hydrogen production, and we can do the things that are typically related to the hydrogen storage processes as well, such as compression and liquefaction of the hydrogen. Right, so the Viva Process Simulation is very good at handling all of the different ways that we do hydrogen production and processing currently within industry. The main way that we are going to focus on doing hydrogen production for this academic competition is going to be through the use of the renewables library's electrolysis model. And so there is an example here, and we're going to open it up later. There's this SS2 example file that you can open and reference that will show you how to use the electrolyzer, right? And so you can see from this diagram here, this PFD, right, that we use an electrical input here into the electrolysis model. Sorry about my tongue getting tied. And then we feed the electrolysis model with water on this side of the model. And when you feed it with the model and you have the electrical input going in, that's going to start to do the conversion into the hydrogen production. And so when you see this here, we have the hydrogen being produced over here, and we have oxygen as well as unconverted water that's being recycled back over here. So this is the water that's being recycled back and the oxygen over to here. Right, so this is the process, and it's pretty straightforward, but sort of what I talked about earlier with the model libraries, this is a combination of both the renewables model library for all this electrical stuff and for the electrolysis model itself, and then process model libraries. This is a process source, valves, mixer, This is a drum that's used up here, process model sinks. So you do have to use a little bit of both libraries to properly simulate this entire process. All right, so let's talk a little bit about the renewables models themselves. The wind farm model is used to calculate power based off of how many wind farms you have. And so this one model itself can have multiple turbines in it. Right, so there's this N turbines parameter here. You can change it to have multiple wind turbines just for this one wind farm. And then on top of this, it uses several different variables that we see here to calculate the power that's calculated. So let's see, here's the power, which is represented as just P, not power like it is in pump or some other process model library models. Right, so don't get confused. This isn't pressure, this is power. And if you hover over this, it will tell you that it's power. Okay, so that way you know. All right, but there's a couple different variables that go into the calculation of the power. Typically, it's going to be the air density, the area of the blades, the wind velocity, and the power coefficient. And so when we use the wind farm, we're trying to focus on a couple of these specific properties to maximize the power that's coming out of the wind turbine. The main ones that we tend to manipulate or work with the most are going to be the wind velocity and the power coefficients, right? Because there's a couple different factors that go into both of those, right? A lot of these other things are information you get straight from the physical information about the wind turbine, right? The blade has only so much area, so it's not like that's going to change. The density of the air is going to be a certain value, so it's not like that's going to change much, but velocity can change throughout the course of the day and even throughout the course of a year, different times at different points in the year, right? And so we can use velocity curves, which you'll see in the next slides to come, to represent different velocity values at different time points, right? And we can also utilize other factors to affect the calculation of the power coefficient. And so there's a couple things that we can manipulate here that we can work with to create the wind farm that most optimally produces the most power. All right, so here's one example. There's power curves. So power as a function of the velocity, right? And so you can see there's a default curve here that is typically used in the wind farm. This one here goes up as the power goes up as the velocity increases. At a certain point, you've reached the max amount of power that you can get at any speed within this range here. And then you'll see this dip here because most of the time these wind farms, when there's a certain velocity point where it's higher than that point, it becomes unsafe for the wind farm to operate. And so they'll shut down the wind farm so that it's not blowing at such a high speed to protect it from any damage that may cause. And of course, when it's shut down, there goes your power, right? So you'll see this dip a lot of times. And so this is a pretty standard curve for this relationship, but you can use your own curves as well. Using the performance curve capability that we talked about earlier, you can create your own curves that have their own relationships. The power coefficient variable, that CP variable, this tends to be a function of the blade tip speed ratio and the blade pitch angle. All right, so we can try to maximize this by adjusting these two variables. There's, according to a specific law that's been established, all right, Betts's law, there's about an upper limit of 59.3% for these. So there's only so high you're going to be able to go with this power coefficient to be able to that factor in the power calculation. And the other thing you have to also realize that this is typically calculated by a Viva process simulation. So you're not normally going to be specifying this. It's going to be based off of these other conditions. Here's an example of the change in the velocity over the course of a day, right? So we can set up a velocity curve at different times throughout the day. And so you have different velocities as the day goes on, right? And then this can be utilized in the dynamics. So if you have a curve like this, when you're in process mode, you'll use an average velocity that you'll either specify or have it calculate based off of one of the other conditions, right? And then in dynamics mode, when you switch over, it'll use the curve instead. And so you can actually run this out over a 24-hour period within APS, and you can see how the power calculations change depending on these changing velocity values. All right, we do have this source here that you can reference for wind resource data at different areas in the US. I believe you can access that straight from the model itself, the help documentation. So let me get open that first example real quick. So here's the renewables library. If you right click and you go to help, you should be able to find that information here. Let me see. Thought I saw a link to that, but I guess I do not. Okay, let me pull this up real quick, and then you guys will have it in the recording. Okay, I'm going to push this into the chat, and that way you guys have it. Okay, moving on. The next model we're going to talk about is the solar farm. One of the things about the solar farm is you can have many different panels as well for this, just as you would have many different turbines for the wind farm, right? And so you can increase the number of panels to increase your power that's calculated for the solar farm. Power is typically a function of these factors that you see here. So panel area, solar irradiance, performance ratio, the efficiency of the modules itself. And then even though it's not shown in this, there's an impact from cell temperature and temperature coefficient of power. All right, so these are the typical variables that we look at, that we work with when we're working with the solar farm. And just like the wind farm, some of these, they're kind of straightforward. You're going to get them from the manufacturer information, and you're just going to set it and that's it. Whereas others, they're going to be things that you can work with, you can change, you can adjust a little bit depending on where you're located or time of the day and so forth. So we're going to focus mostly on the things that you can work with and see how there's variability in the power calculation from those. So the first one here is the performance ratio factor of that equation. This is basically a variable that allows you to account for any losses that are not measured by the manufacturer. So this could be everything from soiling on the panels, shade over the panels, snow on the panels, how old the panels are, degradation over time. You can see there's a whole section for losses, right? And you can factor those in. They add up to a total for the losses, and that's going to effectively go into the calculation of this performance ratio that then goes back, as you see here, into the calculation of your power, right? So for all of these that you have, the more of these that are incorporated, the less power that's going to be produced from the solar panels, right? we use default values for all of these. So you can see there's a default next to all of these, and these are the values. You can change these. You're welcome to change them to whatever values you need to use. We get our values from the National Renewable Energy Laboratory, but you may have a different source depending on where you end up getting your information from. Solar irradiance, which is the H variable in the solar panels. This is similar to the velocity, the wind velocity in the wind turbine, right? So at certain points of the day, the sun is going to be at a better angle on the solar panel and or project more onto the solar panel than other times of the day. And this is a typical solar irradiance plot throughout the course of the day. Now, if you look at it, it makes 100% sense right away, right? If we're at midnight, there's no sun. Sun starts to come up around this time, which we'll say is 5:30, 6 o'clock, something like that. Starting to come up. You're getting more and more power because there's more sun. About midday is your high point, and then it comes back, and around sunset, it's going down. Eventually, it goes down, it goes away, no more power, right? It's pretty cut and dry as to what this means, right? But you have the ability to create these graphs. And so just like you did with the velocity graphs in the wind farm, you can create a solar irradiance graph where in process mode, it just uses the average solar irradiance, the H variable. But then in dynamics mode, it uses whatever the curve is that you have implemented to use the correct solar irradiance value at that point in the day, right? So that's another thing that you have the option of being able to do within the software. I'm going to open this and copy this into the chat as well for your reference. Okay. All right. The last model that we're going to focus on here in the renewables library before we just go and open the software is the electrolyzer. And so the electrolyzer is the model that's going to produce the hydrogen and oxygen as a byproduct from water and electrical input, right? So it's optional to have the electrical input. If you don't have the electrical input, you could still do the electrolysis, but then you have to enter in some conditions manually that would normally be being provided by the electrical input, right? So just be aware of that. The electrolyzer model can represent electrolysis, sort of operations. So we can do a proton exchange membrane, so PEM electrolyzer, or an alkaline electrolyzer. Right, so there's two different options for you. You'll find, I think, that the academic example is a PEM electrolyzer, and so it's going to follow very closely, I think, to the way that the example file is set up. So you should see how you should be able to see how that's set up and done by referencing the example file that I have open. All right, and then there are a couple different properties in the electrolyzer model that are represented through submodels. And so these are sets of calculations that are used specifically for these calculations. And each one of these model types, the PEM and the alkaline type, have their own type of submodel that goes and is associated with these different pull downs, right? So when you're working with the software, you define the way that the electrolyzer operates through the use of the proper submodel selections here. And I think the default ones are set up to be a PEM memory. So you'll see that when we go into the software. You could theoretically create your own submodels and use those for these different calculations as well. So when I look at this here, this is the data entry window here for the electrolyzer model. And you can see here are those three different selections that I talked about, right? So for the, I'll have to reference the terminology, ohmic over potential, open circuit over voltage, and activation over potential. And that's what these different options are here that you see. Right, and you should be able to probably leave these at their defaults. I don't think anyone's going to need to change them for this academic competition, but they're a major part of the way that this model is set up. Right, so do need to understand that. Right. Some of the other key characteristics that you're going to find in here: number of cells. That's this NC parameter. Right, so you can change that. The current density on the electrolyzer stack is the J variable down here. So that's another key one that you'll end up changing quite frequently. And then you can see down here, here's the power that's required for this. You can see the conversion of the water. So this is conversion into hydrogen and oxygen, right? This is typical of what you would see in a reactor when you look at the different variables for the conversion in a reactor. But here we only have water that's converting, so it's just written as X-H2O, right? And then you have some other areas for other concerns that you see in here. But typically where you're going to be focused in terms of your results are going to be on your product streams themselves. And so you have your sinks here, and you're going to be looking at them to see how much hydrogen, how much oxygen is produced. The electrolyzer, if you are going to have the electrical input, it requires DC input. And so you have to convert, if it's in AC already, you have to convert it to DC. We have a model called a rectifier that does that conversion. Right. And then the other thing that you'll have to be aware of is that you might need to step down the DC voltage. Then you can do that using a converter. All right. And so that's another model that's in the renewables model library. So you'll see those in the renewables model library, and you'll see them in the example file. Here are some more electrical related models for your energy grid. All right, so typically these first four are used to convert or step down or step up the current from one type to another. Right, so if you need to step up or step down from AC to AC or DC to DC, you would use a transformer or a converter. If you're looking to change the input from DC to AC or AC to DC, you would use an inverter or a rectifier. If there's points where you want to, take into account certain information along the grid, you could throw in cables to there. You can use bus bars, breakers, generators for additional energy input that comes maybe from some other type of source, right? Instead of it being a solar farm or a wind farm. Let's say it's a normal generator from a normal plant, right? You want to represent that into your electrical grid, you would use the generator model. Right, so there's all these other models that are available to you as well. So that's everything in the slides that I'm just going to show. Let me open the software and go through some of these examples real quick. So we have our renewables library over here. You can see here's the wind farm, solar farm. This is a battery if you want to store energy. Here's your electrolyzer. There is a rigorous electrolyzer. You should not need to use this for the academic competition, but typically this is used for dynamic simulation of an electrolyzer. So this is a much more advanced version of the electrolyzer model. And then you have your other various models that I was talking about: cables, bus bars, transformers, converters, inverters, rectifiers, breakers, your resistor here. This is a generator for some simple external generation, some energy consumers. There is a green H2 fluid, green hydrogen fluid. It's a fluid that already has water, oxygen, hydrogen already created, uses SRKM for the thermo method. And this is what allows you to quickly and easily get set up with the electrolyzer so that you don't have to create your own fluid. If we come in here, we can see it's using that fluid, even though it's a process source, right? It's using the fluid here in the renewables library. So the electrolyzer is only ever really going to use this fluid. It doesn't need any other fluids. So we have this pre-built fluid for you that you can quickly utilize. Here are some sample curves for wind, solar. This is for power, the power curve for the wind farm. You can use these as starting points to make modifications, or you can create your own curves. And then these are just some submodels that are used in these other models. These are actually the submodels used in the electrolyzer model here. These models here. All right, inside the simulation that we're looking at here, you can see here's my solar farm, right? Using the irradiance curve right here, right? And we have area specified, efficiency. We have this is our coefficient of power for the cell temperature. This is our solar irradiance, right? Cell temperature. And we can swap these, right? We don't have to have those conditions set. If we wanted to, we can have it calculate solar irradiance. Instead, maybe we calculate or we specify what the power is supposed to be or what's needed and have it back calculate solar irradiance, right? So just like any other variables, we can swap these around. The program knows the relationships. It knows all the equations. It knows how they're all related through those equations. So just like any other model and any other model library, we can swap things around if we needed to, right? Maybe we need a certain hydrogen production, right? We can specify that. We can come into other models and say, you know, tell me what I need in order to achieve that, right? What kind of conversion do I need in the electrolyzer? What kind of, what's my area that I need in order to get that, right? How much more power do I need by changing the area, right? So we can swap things around and work with this in order to meet the needs of whatever our design is, whatever we're trying to achieve. Mm-hmm. You can see here the solar farm is going to be in AC, or it's going to be in DC, and then it's going to convert from DC to AC to go through these first couple things, and then we're going to convert it back to DC, and we're going to step it down before it goes into the electrolyzer. All right, so this is really the big point here, these two right here. But we first converted it over to AC for a couple of other considerations over in these areas. Okay. The makeup here, like I said, it's a process source. We look at a bunch of these other models, they're all process models. So process drum, process pump. The sinks are process sinks, right? So you do want to make sure you open up the process model library and use the models accordingly. Okay. And then the electrolyzer, you can come in here. This electrolyzer is pretty straightforward. 20 cells. There's a certain pressure drop. Here's my current density. The conversion that I'm asking for excess water fraction. I'm sorry, this is not conversion. I was misled. This is the excess water fraction. So I guess this is to ensure that there's still a little bit of water afterwards. I'm not an expert on renewables, so I'm not sure 100% why this is specified or necessary, but it says it a little bit up here. Since the electrolyzer operates with an excess of H2O, an additional recycle loop is modeled to so they might have this specified here for this file just so that they can ensure and show a recycled amount of water coming back into the electrolyzer. So that's probably the purpose that this specific setting is serving here in this file. This may not be required in yours. Just depends on how you want to go about setting it up. All right, with that, we're at 3 o'clock. I thought I was going to end sooner. I apologize for that, but that's pretty much everything. We're going to open it up for questions. So if anyone has any questions, feel free to ask.
We have two questions. The first one I try to answer, but I think it's better you to show this in the process simulation.
Okay.
And the last one I was trying to answer, but you finished, so I let you to show this also.
Okay. Does the help documentation of the models contain information about the equations for all simulation modes, or does documentation differ between process, fluid flow, and dynamics? So it does, it shows you everything for the model in sort of a general sense, right? So if I go and I open up this help documentation here for this drum, right, it's telling me about the drum, how the drum typically operates. There may be parts where it says, in process mode and gives some stuff, fluid flow and dynamics behave this way, right? So there might be bits and pieces of information like that throughout. But what you're not going to find in this help documentation most of the time is actually the equations. Because the program is open, we assume that if a user wants to see the equations, they're going to right click and go to edit, and they're going to view the equations directly from the way that the model is edited and track things down through this means, right? So the help documentation itself tends to be more general and get into more like theory and talk about key pieces of information like key parameters, key variables. You even see the default spec status of different variables in each of the different modes. It highlights those as well. You could see here's some, sort of concerns. How do you set a level transmitter for the drum? How do you handle port elevations? So it talks about different things like this, but you don't see equations, right? Because we are assuming if you want to see equations, you go into the editor window and you browse and you find out how things are calculated that way.
Perfect. And there is a last one.
I believe you are doing things in APS, but we can only see your PowerPoint. I hope that wasn't an issue for everyone. I only have one screen. I don't have multiple screens, so everyone should have been seeing the same exact thing I was seeing when I was looking at it. So hopefully that was not a problem.
I think it was some delay.
Okay. Are the default values for ohmic and activation over potential based on specific electrolyzers, or are they taken from literature? Good question. So I want to say they're based on something, because everything that we have in the software is based off of either some kind of literature value or some resource that has been researched and validated. As far as I know, we don't put in information or values that don't come from some kind of supported source. I'm looking here to see if there are references. Okay, so sometimes when you look at these model documents, these help documents, they will have references at the bottom and tell you the sources of where we pulled the information for various information. So this talks about the electrolyzer itself, which may potentially talk about some of the submodels that are used. But oftentimes when you want to learn more about the submodels, you might also have to go to the submodels documentation, and they might have something here. In this case, I'm not seeing anything, but I do see this pop-up, which tells me a little bit about it here as well, right? And so, and this, I can't move to highlight the part of this pop-up I'm talking about, but it says some options are also available in the renewables library. It says volt, alk, volt, PEM, right? Those are for the different ways of setting up the electrolyzer to be alkaline electrolysis or proton exchange membrane. So there's a little bit of information here that we can reference. I'm still not seeing exactly where those sources of the information are directly from here. So hopefully it's one of these resources that's telling you that information. Other places that you occasionally find this information is by looking at the editor window itself. Sometimes when you look at equations that are used, or even variables and the way that they're defined, you'll have information in the description that tells you where it was pulled from, what the reference is for that. Fortunately, I'm not seeing that yet again here.
Richard, correct me if I'm wrong, but I think that those variables are being calculated, because if you open the full properties window, I saw that both of them are being calculated and not because the checkbox is unchecked. So if you see
but they're calculated based off of something, right? So I think what she's asking is for a reference on how they're being calculated. Like, what is the source that we use for literature for these equations, right? There's equations here that calculate that, right?
Yeah, there's no standard values.
Yeah. So what are these? Where are they getting these values? Is I think what her question is. And I'm having a hard time tracking down where they're coming from. That's more of a straightforward equation. I don't see any reference information though for literature. Is it possible to know the efficiency of the electrolyzer in the production of hydrogen? So normally we would have efficiency as eta as a variable in most models. With these renewables models, I'm not entirely sure which which things are which when I first look at them. So I'm hovering over some of these, but I don't see anything that seems to indicate efficiency per se. I think the easiest way, if you want to gather an efficiency, would be to reference the products, right? If you reference the products, you can look and you can see, how much hydrogen, how much oxygen is coming out, and that'll give you an idea of how efficient it was. You can even set up some basic calculations using flowsheet equations and set them up on here to calculate an efficiency based on those values. Tomorrow, we're going to talk about how to use flowsheet equations, so we'll see that more tomorrow. So, empirical relationships, that's why I was at, but if some sources are referenced, I can figure it out. Thank you. Okay, yeah. So what we can do is we can follow up on this and try to see if we can get a reference for where those submodel information is coming from. So I'll try to track that down and see if I can get that back to you. Are there any other questions for today?
I don't think so. Everybody is quiet. So thank you very much for this session. And we see all of you tomorrow, same time, same link, okay?
Yep. And just to recap for tomorrow, we're going to be doing the economics model library, which is going to be an important aspect of this academic competition. And then we're going to talk about the Excel add-in and a couple of advanced features that you can utilize within the software. Some of these are for sure going to be used in the academic competition. So you're going to want to definitely make sure you tune in tomorrow for several of these topics.
Excellent.
Thanks, everyone.
Thank you.
Thank you.
Bye-bye.
Bye.